This is the video podcast for part 1 of chapter 5 about the human impacts on forest hydrology. And one of the central issues in hydrologic science today is the fact that humans, through the development of modern civilization, have a tremendous impact on the landscape. And that has severely influenced, not only the hydrological cycle, but certainly all aspects of the ecosystem. This is the first of several lectures that are going to look at humans and their role in the hydrologic cycle. But here we're going to focus specifically on forests, and we're going to look at that from different perspectives. Okay, so to achieve that goal, I'm actually going to break this video podcast up into 3 different parts instead of 2, which I do sometimes, because they really are different perspectives on it. So in the first part here, I'm going to introduce the topic of deforestation, what it has looked like, and what are some of the basic consequences of that in terms of wood and water. Second, we're going to look specifically at the relationship between loss of forest cover and water flux based on the water cycle. Then in the second presentation, I will give an analysis of paired basin studies and what we've learned from that special kind of way of addressing the water cycle and the effects of deforestation. And then in the third video podcast, I'll present paleoenvironmental studies, which provide a longer-term context for the changes that have taken place. And in all these presentations, I will be focusing on the United States because this is the context with which I have the most experience and it's relevant to this course. Well, the historical motivation for hydrologists to look at the link between forest cover and water had to do with efforts to try to yield more water for societal use. In general, you can imagine from the water cycle that water is taken up by trees, whether it's through the root system or whether it's taken up, directly intercepted into the canopy. And so through the processes of interception and transpiration, a significant amount of water is lost. Anywhere from 30 to 70% of the water that rains out of the sky is, evapotranspired away. So the conceptual idea would be to cut down trees, and in the process of cutting them down, then that could also yield to greater water as runoff that could then be used, that superficial water or groundwater, that could then be used by society. As an interesting side note, if you consider snow, the role of vegetation on snow has 2 different parts, and this is just a side note, but conceptually, you could imagine that trees would shade the snowpack, and we'll actually be looking at that mechanism later on in the quarter towards the end. And so maybe trees would help to protect snow from melting. But on the other hand, trees also intercept a lot of water as snow, and then that snow gets primarily evaporated away, though some of it may melt and drip. And so as a result of that, actually cutting down trees tends to, in the net, preserve the snowpack by eliminating the transpiration, the interception component, which is preferentially a larger impact on the snow balance than the benefit that trees provide in shading snow. Also, trees tend to heat the ground around them, and so then that contributes to melting and evaporation. So overall, there's always been an interest in considering deforestation as an aid to water yield for societal use. In modern times, the motivations for evaluating the role of forests and humans on forests has really changed. Today we recognize much more that the landscape and its processes are highly complex, and we need to balance environmental functions with societal needs, and the impacts of humans generally can be quite complex in terms of how they affect the environment. So we need to have better tools, better science for managing the landscape. And so as 3 examples I show here, studying the effects of logging in deaths caused by landslides. So in many parts of the world, they log steep slopes. For example, here in California or in Japan or in China. And then the logged areas tend to yield more sediment, as I'll show with some evidence in the second video podcast. And then that can generate more landslides. Also, as people, over the last 100 years, people have gone from a more rural lifestyle to a more urban lifestyle. That's caused degradation of landscape in those focused urban areas, but it's actually allowed for renewal of forests, and we'll have to see very briefly what the effect of that is on the structure of forests and its composition. But there certainly are impacts of that redevelopment of forests on the fate and trajectory of those populations. And then you think of processes on the landscape that are a result of both natural and human-influenced processes, especially where there's a long history of what we call cumulative impacts. Cumulative impacts means that things that humans did a while ago continue to affect us today. And so over time, humans are doing more and more things, and as that happens, there's a synergy that leads to exacerbated processes or changes under current conditions. And one of the examples of that has to do with fire and fire management. You probably know that the primary strategy for managing fire in the United States has been suppression. And that has allowed larger and larger supplies of fuel, of downed wood, to then be available for burning. What you can see here is a map on the right that shows the boundary water region of Minnesota in northeastern Minnesota. And the top color map shows fire severity currently in the region. The orange and yellows indicate moderate to high severity, green low severity. So then projecting 100 years into the future, you could see either continued fire suppression leading to generally high risk of fire severity or high fire severity, whereas potentially if they were to do some controlled burning that emulated historic fire regimes, try to emulate natural processes, it might be possible to mitigate fire severity to have a benefit. So these are all reasons why hydrologists are involved in studying forests and water cycle influences. Well, we need to begin at the beginning, and in this case, we're going to treat as the beginning the baseline condition that Europeans found when they came to North America. Now, obviously, large populations of North American Native Americans were already here and engaged in landscape management of various sorts, depending on the region. However, through much of the United States, the scope of that was not as impactful as what Europeans did. Europeans fundamentally transformed the landscape of North America unlike what had ever happened before. And so that's why we can treat this as a meaningful baseline, even though important things were already taking place prior to that. So this is a map, and this map comes from the book, which I have right here, called From Coastal Wilderness to Fruited Plain by Gordon Whitney, which is from 1994. The references is in the last slide of this presentation. And it shows the state of the forest as best as can be reconstructed in 1620. So the areas in black are the areas of virgin forests, and the areas in white would be non-forest natural landscapes like grasslands, open water, mountaintops that are devoid of vegetation, and deserts. Also wetland and other kinds of wetlands. So even though there was already some management taking place, some of the things you can see here is first just the density of forest cover as well as the dendritic pattern that you see that's associated with river valleys, and so there's a dense forest around those rivers. Just going from 1620 to 1850, you can see a significant change. This is the period where there was deforestation taking place, land clearance by colonists, and you can see that the land clearance was especially widespread along the entire eastern seaboard, and then also at the boundary, all around the boundaries, especially at the junction on the western end of these eastern forests, and then also through the upper Midwest. Now on the East Coast, by 1850, there was already widespread intensive agriculture that was taking place, so really intensive land utilization. But you could see that in this first 230-year period, there is this reduction around the fringes. The Appalachian Range generally intact, and of course the western forest still in quite good condition. So that was the first 230 years. Now let's look at the next 70 years. Boop. Forests are pretty much wiped out for much of North America. That's a pretty dramatic change that's taking place there over just a 70-year period, because this is when you begin industrialization, and so you have mechanized deforestation taking place at unprecedented rates. Just comprehensive clearance and utilization of the land. To further appreciate the ability of humans to alter the landscape, consider these two maps of the United States. This is from a study done by Hook in 1999 that tried to compare land use derived changes to the movement of material on the Earth's surface, soil, sediment kind of materials, versus what happens naturally, driven primarily by streams and water-based erosion. So in the upper slide there, upper pit map, you see on the y-axis what looks like topography is reflecting gigatons per year. The A means year, so gigatons of dirt moved per year. And the grid that's shown over the map is a grid of the United States where each cell has a number that relates to the kinds of things that are taking place, but especially driven by population. And you can see that humans are moving Earth dramatically all over the United States, with a typical year having 7.6 gigatons of sediment redistributed, whereas natural yield is concentrated primarily where there's high relief, which is the Rocky Mountains or the coastal range, where the fastest uplifting mountain range in the U.S. And so there you have highly erodible sediment, rapid uplift rates, so exacerbated processes, but still, only 1/7 of the impact of what humans are moving around today. In terms of the changes to forest composition, we can see that not only have forests been lost in North America, but what constitutes a forest is different. And this isn't only because of vegetative processes alone, but it also includes the impacts of animals on that as well. So for example, here we have Michigan, and what you can see is that predominantly prior to settlement, the forests were governed by oak, pine, and northern hardwoods. After that, the lower half of Michigan was deforested, and then the upper half was dominated by what are recognized as faster growing disturbance species like aspen and birch, and then you still see a few of the other oaks and so forth, but really the widespread encroachment of aspen birch, or just having no forest at all. And what I meant when I said the role of animals is like if you extirpate all of the wild boar, and deer and other predators, you're going to get a change in the seed bank that's there. So those, if those grazers and if they, organisms that would either eat all of this into the seed bank or that would carry on their fur seeds as a dispersal mechanism, when they're gone, when they've been hunted out, then they're not available to promote that prior occurring process of forest development. When you look at the wood that was harvested throughout the entire United States, you can see that there's been a lot of utilization of wood for a variety of purposes, but plywood, veneer pulp, lumber, and fuel. And what's interesting is that wood as a primary source of fuel was really significant until the Industrial Revolution, but once the onset of utilization of coal took over, then that plateaued and then dropped with hydropower, nuclear power, natural gas, and coal, and also the transport of oil and the use of oil. However, when you look as the amount of wood that has been used for other kinds of production like pulp, paper, and lumber, you can see that there was an initial abrupt plateau that took place from 1900 to 1940, but that since 1940 that has really taken off. And unfortunately, this graph stops at 1980. So I was wondering if the students could take the time, pause here, and go onto the internet and search under utilization of United States grown woods to see what has happened since 1980. From what I've seen from 1980 to 2000, this growth of use of wood has increased because paper has been very important. Now, I'm not so sure what's happened since 2000, so it'll be interesting to see what happens. Like, I myself have dramatically reduced the amount of paper that I use. I hate printing out anything in paper anymore. I try to look at everything digitally. Although then you wonder, well, how does the energy consumption in using a digital source compared to the energy consumption in paper production and recycling. So if you want to look into that, you could learn more about what is the future of the use of wood and potential deforestation in the United States. Well, the main activities that humans do related to deforestation and generating a lot of sediment associated with that include urbanization, road construction through forests, logging, mining, and agriculture. Over the totality of this course, we're going to look at all these topics, but today we're focusing on the road and logging topics primarily because those are the areas in which we'll see what are the hydrological responses. And later in the course, when we look at hydrological models, we will have models that will look at, as you increase roads, what happens to different water fluxes, and same thing with logging. So this is going to be a theme that we're going to return to throughout the quarter, and this is really just the first introduction of this theme. I'd like to show you a little bit of the scientific information that links forest cover and loss of forest cover with water flux. As I said before, the concept is that trees intercept water and they transpire water, and as a result, if you cut them down, then that should yield more runoff. So is that actually observed? Like, what do the actual scientific studies show? One method that you could do to look at that would be to measure forest cover in many different watersheds using remote sensed imagery, and then do a steady state monthly or annual water balance. So something like gross precipitation equals stream flow plus ET. I've shown you already an example, I think, in the validation of the Penman-Monteith equation, a water balance like this. It neglects the groundwater flux and just looks at surface water balance. And so then can you see, if basically by measuring PG and estimating ET, can you get a relationship between Q for a watershed and the percent forest cover and see what you get? As an illustration, there was a paper in 2011 by Wang et al., and it showed different regions of China, and I'm just showing two of those regions, the Loess Plateau and Northeast China, that show opposite results. The results for the Loess Plateau are what you'd expect. On the x-axis, forest cover goes from 0 to 100%, and on the y-axis is the runoff coefficient, which is essentially what percent of water runs off, or I should say what fraction, because that's a fraction. And so these fractions tend to go from 0 to 16, 0.16 or 16% of the water. So if we look at the Loess Plateau, you can generally see that there is of course a correlation here with an R of negative 0.64. That means that since it's a negative relationship, as forest cover increases, the amount of water that goes to runoff, or the fraction of that, decreases. You can also see that a p-value here of 0.05. What does that mean? If you've taken statistics, that's telling you that there's a 95% confidence that this relationship is statistically significant. However, beyond statistical significance, I like to do a little bit of a scientific significance. And so what I would tend to do is I would look at this and say, let's take the middle of the pack here by 0. And if I draw a straight line across, I can get almost to 60 to 65% forest cover with no change in runoff coefficient. If I come to the bottom, lower end here, around 4% runoff coefficient, I can go all the way across from 0 to 100% with no predictive capability of forest cover. So in general, if we cut this data in half, if we took the average of the results from 0 to 20%, we would have a higher runoff coefficient of about maybe 8%. And then if we took the data from 60 to 100%, we would have a result of about 3 to 4%. And so it's really the difference between those two end members more than saying that there is a clear linear relationship here. So in general, a very low forest cover has a higher runoff percent, and a very high forest cover has a low runoff percent. But I'm not so confident in the robustness of this statistical relation. In any case, if we look at Northeast China, it's like, what? What is this thing doing? It doesn't look anything like the Loess Plateau. In fact, not only that, as forest cover increases, the runoff coefficient is increasing. I'm not really sure what that means. What do you think? Well, of course, I've actually read this paper, so I have some idea to know what Wang et al. Thinks. And what they think here is that there's a little bit of a trick going on. Yes, runoff is increasing as forest cover is increasing, but That's because the most forested areas in the northeast China region happen to occur at high altitudes where they have more precipitation and less potential evapotranspiration. So in this case, it's not so much an actual relationship between forest cover and runoff with all other things being equal. That's the key. Nothing is equal. In fact, in this case, we have significant differences from dot to dot to dot on this plot, and as a result of that, it's really showing a spurious correlation. That's like we could find a correlation between, sunspots and SAT scores, but it's very unlikely that there's any real mechanism or actual causal mechanism between sunspots influencing SAT scores. So here what we see is that as forest cover increases, we have actually an even stronger relationship, but it's positive, statistically significant, fewer points, just 22 compared to 72, and the runoff coefficient increases as forest cover increases because other factors are controlling that, and this just happens to be, forest cover is just going along for the ride. So what this shows us is that you have to be careful with these kinds of relationships, especially when you're doing it at a regional or global scale. You have to control for things like geology, climate, topography, land use, soils, and so forth. Here's another example where we look at a single region, and in this large catchment, we have a relationship between rainfall event size and peak discharge. So we have this one catchment, and we can see that there's a relationship that bigger events are producing more water. Well, it turns out that before 1978, this catchment was predominantly agriculture, and that after 1978, forest plantations came in. And actually afterwards, more than 30% of the watershed became covered with forest plantations. So if you look at the open squares, you see the relationship, and now this is R squared, not R. So 0.6, that's a much more robust relationship than what we saw from the China data. And then you can see that as you go from agriculture to forest plantations, the peak discharge decreases significantly. So for example, for a rainfall event size of 10 millimeters, we go from about 90 cubic meters per second down to an average of about 10 cubic meters per second. So it's a significant effect on storm magnitude. The curious thing that you have to think about, though, is that these two lines are not parallel. In fact, they converge. So for small rainfall events, we see a much larger effect of deforestation, or having forest versus not having forest, compared to large events. So I'd like you to think about why would that happen? Why would large floods not see a difference in forested versus non-forested catchment conditions for the same catchment? And we can talk about that during class, or you can try to think about it on your own.